We've now seen how to set up cylindrical coordinates and spherical coordinates to specify points in 3D as alternatives to the more familiar Cartesian coordinates. And we looked at the more intricate details like finding the volume elements and surface area elements, which will be needed later on when we come to volume integrals and surface integrals. However, cylindrical coordinates and spherical coordinates are still not the only way to specify points in 3D space. There are also paraboloidal coordinates, oblate spheroidal coordinates, prolate spheroidal coordinates, toroidal coordinates, bispherical coordinates, conical coordinates. You get the idea. There are a lot of different coordinate systems, and we're not going to look at any of these particular other systems in detail. However, all of those systems I've just named, including Cartesian, cylindrical and spherical, are all particular examples of what in general is called an orthogonal curvilinear coordinate system. Let's have a look at what that term means. Curvilinear means that the coordinate axes aren't necessarily straight lines but could be curved. For example, consider plane polar coordinates in 2D. On this picture we can see the Cartesian x and y axes, but where exactly is the r-axis or the theta axis? Does that even mean anything? Well, yes. Imagine firstly that we fix the value of theta and let r vary freely. What will happen is that we will trace out a half line. Theta has the same fixed value for every point on this line, but r increases as we move along this half line away from the origin. So in a sense, this half line is the r-axis for this particular value of theta. On the other hand, if we fix the value of r and let theta vary freely from 0 to 2 pi, we'll trace out a circle of radius r. This circle is, in a sense, the theta axis for this particular value of r. Of course, this time the axis isn't a straight line, so rather than calling it a coordinate axis, we tend to call it a coordinate curve, but it doesn't really matter. But that's what curvilinear means. The coordinate axes can, in general, be curved. But sometimes they can still be straight lines too, like with the r-axis, and that's fine. We still call it curvilinear in general. What about the word orthogonal then? This is all to do with the unit basis vectors, and as the name suggests, it means that they are orthogonal. So if we first of all consider 2D Cartesian coordinates, the unit basis vectors are simply the unit vectors that point along the coordinate axes. For historical reasons, we usually call them I and j. Notice that the angle between them is 90 degrees, so they are orthogonal. Notice also that these vectors aren't tied to any particular point in space. We can move to a different point and the I and j vectors still exist there and are the same as at every other point. Now let's go back to 2D polar coordinates. At some particular point P with polar coordinates r and theta, we can find a unit vector that points in the direction of increasing r, with theta held fixed, and another unit vector that points in the direction of increasing theta, with r fixed. We call these vectors ER and Eθ. Note that ER points along the r-axis, but as for Eθ, since the theta curve is actually curved, we can't say as such that Eθ points along the theta curve, but we can say it's tangential to the theta curve at the point P. Note also that ER and Eθ are at right angles to each other, orthogonal. This is why we can say that plane polar coordinates are an orthogonal curvilinear coordinate system. Curvilinear because we may have curved coordinate axes, as happens with the theta curve. Orthogonal because the unit basis vectors are at right angles to each other. The final thing I'll point out here about the basis vectors is that unlike I and j, which are the same at every point in space, ER and Eθ do actually change depending on what point you're at. They always point in the direction in which that coordinate would increase, with the other coordinate being held fixed. Here are the corresponding diagrams for cylindrical coordinates and spherical coordinates in 3D. You can see that in each system, the three unit basis vectors are mutually orthogonal, so they are indeed orthogonal curvilinear coordinates. We are now going to investigate how we can find the basis vectors, Lamé coefficients, volume element and surface area elements in a completely general orthogonal curvilinear coordinate system.
It is not lame, you are lame. It is Lamé. Lamé, like the shiny fabric.
Okay, Lamé.
Right.
First up, the basis vectors. If you think back to the beginning of our study of vector calculus, you'll remember that if we have some general curve in space parameterized by a parameter t, then we can find a unit vector that is tangential to the curve at a certain point by differentiating the position vector r with respect to t, and then dividing this vector by its own magnitude to make it have unit length. We can use the exact same idea here to find the unit basis vectors in a curvilinear coordinate system. Suppose this curve is actually just one of the coordinate curves. Let's call this coordinate q1. So q1 could be r or theta, for example, if we were in polar coordinates, or it could be rho or phi or z if we were in cylindrical coordinates, and so on. The coordinate curve is parameterized simply by the actual value of the coordinate itself. So to find a unit vector tangential to the coordinate curve at a certain point, we simply differentiate the position vector r with respect to q1 and then divide this vector by its own magnitude to make it have unit length. So what we've got is a unit vector pointing tangential to the coordinate curve in the direction of increasing q1. That's exactly the vector we want to be the unit basis vector. So instead of calling it t, from here on we'll call it e1. So that's how we find the basis vectors in general. Now we're going to look at the volume and surface area elements and the Lamé coefficients.
Okay, Lamé. Right.
To keep it easy to visualize, we'll start with just 2 dimensions. Consider some point P in 2D space and another neighbouring point P prime, neighbouring here meaning that the distance between the points is infinitesimal. Let the names of the coordinates be q1 and q2. If point P has position vector r and point P prime has position vector r plus dr, then the vector going from point P to point P prime is just the vector dr. Since dr is a vector, like any other vector, it can be resolved into its components. That is, it can be expressed in terms of the unit basis vectors e1 and e2 at the point P. So we can write that the vector dr is equal to the component dr1 times the unit basis vector e1 plus the component dr2 times the unit basis vector e2. Remember that this is an orthogonal coordinate system, so e1 and e2 are at right angles to each other. For reference in a moment, here are the expressions again for e1 and e2. However, since dr is a total differential, we also know that dr is equal to dr by dq1 times dq1 plus dr by dq times dq2. This is basically just the chain rule. Notice that the dr by dq1 and dr by dq2 that appear in this expression for the total differential are related to the basis vectors e1 and e2 as shown here. So by comparing the 2 equations that we have for dr, the first equation being at the top where we split it into components, and the other equation being the bottom one here using its properties as a total differential, we see that dr1 is equal to the magnitude of dr by dq1 times dq1, and dr2 is equal to the magnitude of dr by dq2 times dq2. We now introduce the Lamé coefficients. We define h1 to be the magnitude of dr by dq1, and we define h2 to be the magnitude of dr by dq2. Then the lengths of the sides of the blue dashed rectangle are just h1 dq1 and h2 dq2. The surface area element in 2D is then just the area of the blue dashed box. That is, ds equals h1 dq1 times h2 dq2, which is just h1 h2 dq1 dq2. We'll now look at the corresponding picture in a 3-dimensional orthogonal curvilinear coordinate system q1, q2, q3. Again, we have 2 neighbouring points, P and P', with the infinitesimal vector dr going between them. We've shown the curved coordinate axes emanating from point P, the unit basis vectors at P, and also some dashed straight lines along these basis vectors to help our visualization. If we draw in the cuboid with P and P' at opposite corners, then using the same logic as in 2D, the lengths of this cuboid's sides are h1 dq1, h2 dq2, and h3 dq3. Thus, the volume of the cuboid, which is the volume element, is dv equals h1, h2, h3, dq1, dq2, dq3. And if we want a surface area element for one of the coordinates being fixed, that's just the area of the corresponding face on this cuboid. For example, if we hold q1 constant and let q2 and q3 vary, that corresponds to the left-hand side face or the right-hand side face on this cuboid, whose area in either case is h2, h3, dq2, dq3. The surface area elements for the other faces where it's either q2 or q3 that's being held constant are as shown here. That's everything you need to know about orthogonal curvilinear coordinates.
Brilliant! I have absolutely no idea what's going on.
And if you think this is bad, be glad we're not making you learn about non-orthogonal curvilinear coordinates. I used to teach a level 3 module called tensor field theory where we had to look at that for general relativity, and trust me when I say that you really don't want to see that stuff. In the next video we'll consider how to parameterize surfaces, how to find normal vectors and tangent planes, and the vector surface area elements.
Well, we're boned.